All right, so this chapter, we've already talked about sampling distributions. We're going to move on, use what we know about sampling distributions to talk about confidence intervals. So let's switch this over here and let me name this. Okay, excuse me. So the first thing we're going to look at is set up this idea of what a confidence interval actually is. Okay, so we're thinking about a confidence interval. Most of the time we don't have population data and we can't figure out what that population mean is. Best idea we have is a sample mean, right? So we talked about a little bit, okay, if I get higher sample sizes, I'm more likely to see sample means that are close to the population mean. But what if I have a relatively low sample size? Like what if I only had 10 people and I wanted to know the average income? Is that really, there's a likelihood I could be way far off, right? If I get a millionaire in there, it's going to greatly influence my sample mean. My sample mean might be quite a bit different than my population mean. So what we're going to try to do is we want to try to make sure that sample is a good predictor, right? Or we say an unbiased predictor, right? And then also we want to make sure that we say, okay, look, there are some things we can control that reduce the variance of that sampling distribution, right? Taking a higher sample size. So we want to make sure our predictors that we're using from our sample have a low variance, but also that they're unbiased, right? That they're not really far off from what the true population value likely is. So the general setup we're going to do is, we don't know what the population is, so we take a sample with our best estimate of where that true, I kind of already said all this about this slide, so we're kind of gloss over this, but our end story is the sample mean is the best idea or the best information we have about what the true population mean is. Okay? So I'm going to set up an example to just kind of talk about confidence intervals. So let's say I'm working for a hospital. I'm interested in the mean birth weight of all the, babies born in my hospital. And I'll report this to the CDC or something. But I don't collect it for every single birth. I've only got a handful of births, maybe a random sample of say 100. Well, what can I say using that sample? How can I use that to make a statement about where the true population mean birth weight is? Because I know that, the likelihood that my sample mean is exactly the same as my population mean, pretty unlikely, even if I'm only off by 0.0001, right? So I know that my sample mean, isn't perfect, isn't exactly going to be the same as my population mean. And in fact, if I have a relatively low sample, like I said in the income example, I could be pretty far off. So what we're going to do is we're going to build a range of values where we can say, okay, look, I know that based off of what I know about the sampling distribution and based off of the sample mean that I saw, here's a range of values that I can say with 90 or 95 or 99% confidence that the true population mean or the true parameter of interest here is going to be somewhere in this range. So, what does this level of confidence means? I think it'll make a little bit more sense once I kind of show you a little bit more, kind of relate this to what we're doing with sampling distributions. But you can kind of think about it. It's within this range of values. It is 95% likely that the true population mean is within these, within this range. Okay. So what are we going to do? Well, we're first going to take this sample mean. It's our best guess of where the population mean is. We're then going to go a certain amount below and a certain amount above to create this range of values. All right. So maybe I take a sample of babies. I see the average birth weight is like, I think 3,000 grams or something. I then said, well, look, I know that, yeah, even if I had a sample of 100, that should be pretty close to what the true population mean is, but I might be a little bit off either way. So I'm going to go a certain amount to the left and to the right of that sample mean I saw to kind of say, okay, look, I know that my sample mean is the best guess of where the population mean is, but it's likely going to be a little bit off. I'm going to create a little bit of a window around it, right? Kind of a buffer zone to where I can say, okay, look, I know my sample mean probably isn't exactly the same as my population mean, but the population mean should be somewhere within this range around my sample mean. Right? So how are we going to choose this W, right? How am I going to choose the amount that I'm going to go above and below this sample evidence that I found? Okay. So the sample mean is normally distributed. We talked about this. As long as I get a sample size over 30, it doesn't matter what the distribution of the original data was. We know our sample means are normally distributed. So we can use some information that we know about that normal distribution to kind of come up with how far away from that sample mean should we go to create what we call our lower and upper bound of our confidence interval, right? Okay, so just set up the first example. Let's say I want to build a 95% confidence interval. Right? From the last chapter, we know that if I looked at a sampling mean distribution and I went 1.96 standard deviations to the left, right, or below that population mean, that there's a 0.025 probability or a 2.5% chance that I see a sample mean that's this far away from the true population mean. Okay? So just to kind of set this up, give a visual here. Oh, I gotta make sure my light's on. There we go. All right. Rolling on paper here. So, wait, is this going the right way? We'll find out. I think I want to flip this and then flip this. Okay. So what we had from last chapter is we said, okay, look, I know that if I can get a sample size over 30, my sample means should be normally distributed around whatever that true population mean is. However, I can only take, or I can't only take, but let's say I only have one sample. I could see a sample mean over here, over here, over here. But what I know is if I looked at that standard normal table, right, and I'll do this, show you this here in a second, go to the table and also show you in Excel. But I can look up, okay, if I'm 1.96 standard deviations, and here we're looking at the distribution of our sample means, so it's the standard deviation of our sample means. If I go 1.96 standard deviations below, right, the area here is going to be 0.025. Right? So the reason why we know this, well, remember, if I'm 1.96 standard deviations below the mean, that's the same as a z-value of negative 1.96. I look that up in the table, and I find the area, the cumulative probability, or the area to the left of it is 0.025. Remember, we started out, we wanted to have a 95% confidence interval. Well, if I go 1.96 standard deviations below, and I then went 1.96 standard deviations above, well, what would the area have to be over on this side? Symmetric distribution, right? This normal distribution. So, or think differently, we could say a z-value of 1.96, we should get 0.025 here. So in between these two values, there is a what? 0.025, 0.025. So the likelihood of seeing something in between 1.96 standard deviations above and below, 0.95, or a 95% chance that we see something within 1.96 standard deviations of that true population mean. Okay. Okay. So I then want to show you, just because you're taking me at my word, I guess, at this point. And I'll come back to this here. This is kind of what I drew out. Here we go. So if we were to look at that standard normal table, so this was the idea of, okay, how many standard deviations away do I need to go to get that area of 0.025 in each of my tails, which then adds up to that 0.05, giving me 0.95 or 95% in between those two z values. So if I want a 95% confidence interval, it kind of gets split up, right? The area that's not in my confidence interval would be 0.05. It gets split up in these two tails, so 0.025. So here I know the area I want in the tail, or that cumulative probability is 0.025. So I got to hunt for it. Looks like it's right here, corresponding to a z-value of negative 1.96. Now I'm going to kind of try to use this table a little bit more in this chapter and the next, although, you can use it, but we can also use, here I got this set up to show you later, but we're just going to open a blank here. I'm going to zoom in so you can see what I'm doing. We can also say, okay, look, if I use the norm.s.inv function, if I know the area I want in that left tail, that cumulative probability is 0.025, I can just tell that norm.s.inv function that, and it returns to me that value of, notice here, I mean, very, very close, but basically negative 1.96, right? If I'm a little bit off here, but it's going to round to the second decimal to that same value. So I can use Excel and be very precise, or I can use this table. I find the area that I want in that tail, cumulative probability. I then find the corresponding z-score, or z-value, sorry. So I kind of drew this out already, but you have kind of a reference to go back to. I know that if I go 1.96 standard deviations above and below that population mean, there's a 95% chance that when I take a sample, I see a sample mean somewhere in this range. Okay. So if I think about this, anytime I have a sample mean that is less than 1.96 standard deviations above and below that true population mean, if I were to build a confidence interval around that sample mean by going 1.96 standard deviations below, 1.96 standard deviations above, well, notice if the value isn't 1.96 standard deviations below here, like it is below the true population mean, but it's only like, I don't know, just to put a number to it, about, I don't know, maybe this would be 0.5. Well, if I then add to it 1.96 standard deviations, negative 0.5 plus positive 1.96, I'd be somewhere at like 1.5. Notice that upper bound, my population mean, is somewhere now in my confidence interval. And then what if I saw a value that was above the population mean? Well, this looks like it's about 1.5 standard deviations above. So if I then subtract 1.96 standard deviations to get my lower bound, positive 1.5 minus 1.96, I'm going to have kind of like a negative, be a certain number of standard deviations below the population mean. But notice my confidence interval here includes that true population mean. So for every single sample mean in this range, right? Oh, I didn't want to show you that. Oh, here we go. For every single sample mean in this range, all of them would have a confidence interval. If I'm using that 1.96 standard deviations to go above and below, they're all going to include what that true population mean is. Well, remember, what was the likelihood I see a sample mean somewhere in this blue range? 95% chance, right? Or a probability of 0.95. Now, so my confidence intervals will include the true population mean for 95% of the sample means that I see. Now, if I see something that is more than 1.96 standard deviations, right? So let's say I take a sample and I see something that's like, what, I don't know, 2.3 standard deviations below, something like that. Well, then when I add 1.96 to it, it's still going to be a certain number of standard deviations below that true population mean. Notice for all of the sample means in this range, when I create my upper and lower bound, my population mean won't be in that confidence interval. So that means that for all of these sample means in this red range, they will have a confidence interval that doesn't include the true population mean, or essentially my confidence intervals will be wrong. Well, what was the area in both of these? 0.025. So I'll have a probability that I'm wrong of 0.05. Now I'm going to be right with a probability of 0.95, right? 95% of the time, but 5% of those sample means my confidence interval would be incorrect. Okay. Let me think if there's anything else I want to say here. So that should kind of set up the idea for us. Just some terms we'll start talking about. So when I say 95% confidence interval here, that was that there's a probability of 0.95 that I see a sample mean that when I create the confidence interval, it will include that true population mean. So alpha is going to be what we say is the probability that I don't have a confidence interval that includes a true population mean. So here, alpha is going to be 0.05, right? So, excuse me, I'll just kind of go here and kind of walk us back. But if we have an alpha of 0.02, or sorry, 0.05, that's 0.025, like on either side of our confidence interval, right? Or in either tail, that adds up to, 0.025 on each side. Excuse me. If we go back and look at that table, we looked up 0.025, we found a corresponding z-value of 1.96. Same kind of idea. Let's say I want to do the 99% confidence interval. So now I know the probability that I'm in between this lower and upper bound it should be 0.99, which means the area outside of my confidence interval, 0.01. So if there's 0.01 total on each side of my confidence interval, I'll divide that by 2, right? Actually, here, can I, no, where's the zoom button? There we go. Oh, I got the spinning wheel of death here. All right, there we go. So 0.01 is the total area on each side, or like total area outside of my confidence interval. So that means each side has 0.005. So for the 99% confidence interval, I look here, okay, where's 0.005? Looks like it's in between these two values. So in between what? Negative 2.57, negative 2.58. So I could kind of split the difference 2.575, right? Or if I did round it up to the second decimal, I could kind of use negative 2.58. So that's how we kind of look up different confidence intervals, right? Different alpha values. The ones that I will reference as our conventional levels of confidence are 90, 95, 99%. Now, we also would say, we could work in either direction, right? So if I know alpha, I can figure out the confidence interval. If I know the confidence interval, I can figure out alpha, right? So if my confidence interval is 90%, that means there's 0.1 outside of my confidence interval. That's my alpha value. If I know that the alpha value is 0.05, I know that means that there's 0.95 within my confidence interval or 95%. Okay. So what we're going to do, the formula for this confidence interval will be that we'll take whatever sample mean value we see. We're then going to add to it a certain number of standard deviations. Well, how many standard deviations away did we need to go? Well, what did we do? So I took whatever my alpha value was, so 0.05. If I had the 95% confidence interval here, alpha was 0.05. That was the probability I saw something outside of this range, which means that I have half of alpha on each side. Right? That's how we looked it up. Okay, so I wanted 0.025. That's how I found that I needed to go 1.96 standard deviations below. That's how I found this z value, or this z value corresponds to what z-score would give me alpha over 2 in each tail, right? And when we look it up this way, when you look up alpha over 2, you'll always find the negative value. It's just that when we build a confidence interval, we're going to go a certain number of standard deviations below to get our lower bound. And then we're going to go a certain number, that same number of standard deviations above to get our upper bound. Now, when we're building the actual confidence interval, we don't have the population mean. We're building it around the sample mean that we saw. Okay. So that's the general idea. That's the general setup. Got return here. So I've got kind of everything labeled here. Now, just also to point something out, notice this is the standard deviation of the distribution we're looking at, which was sample means. So really to calculate this, remember we have to take the population variance divided by the sample size and then take the square root. So we'll kind of see this. I'll go through some Excel examples and some regular examples, and I think this will make a little bit more sense here. Okay. So what's going to change our confidence interval, right? Well, if I have larger alpha values, right, what's that going to do to my confidence interval? So if I think about, let's say I had, and I'll think about the z value then. So remember, so we've got my standard distribution. Let's say I wanted the 90% confidence interval. That means that the total area outside of my interval would be 0.1. That means that there's half of alpha in each tail, or 0.05. If I go to my table and I look this up, and I'll kind of show you this here in a second, negative 1. Let's see if I remember this off the top of my head. I think it's 1.65 standard deviations above and below would give me that area of 0.05 in each side. So then if I think about, okay, when I'm building my confidence interval, I'd be using 1.65, right? Adding that many standard deviations to get my upper bound, subtracting that many standard deviations to get my lower bound. And then that would be that form. Now, if I wanted the 99%, right? We just looked this one up, but if I wanted the 99%, what would my alpha value be? Well, 0.01, which means half of alpha in each tail would be 0.005. If I look that up, I'm going to find that, well, if 1.65 gave me an area of 0.05 in the tail, I'm going to find some value that's greater than 1.65. In fact, I think it's going to be 2.58. So now, if I'm thinking about building this confidence interval, what's going to happen to the width? Well, I'm going a higher number of standard deviations to the left and the right. So whenever I have lower alpha values, my confidence interval is going to get wider. I think the way I have it phrased on the slides is, okay, well, what happens if alpha gets larger? Well, alpha goes from 0.01 to 0.1, right? It gets larger. My confidence interval I'm actually going to be getting is, I guess, more narrow or smaller, right? So that's one of the things that kind of changes our confidence interval. The second thing is a little bit maybe less clear. So let's now assume we're not thinking about the level of confidence. We're going to keep that the same now. So let's say we're just still only looking at building a 90% confidence interval. Okay? So we said, okay, what's that going to look like? I'm going to go 1.65 standard deviations above to get my upper bound, 1.65 standard deviations below to get my lower bound. Now, the size or the width of my confidence interval doesn't change if I see different sample means. All that does is shift that confidence interval. But there's two other things that can change the width, right? So if I actually write this out, and if I'm doing this more generally, here I'm using that z value associated with alpha over 2, but just to kind of keep alpha constant here to make this point, we just kind of kept it with alpha being 0.1. So what is this equation? Well, it's actually going to be the square root of the population variance of the data I'm sampling from, or the observations I'm sampling from, over my sample size. So notice what happens if my sample size goes up. Well, if my sample size goes up, what happens to this fraction, or what happens to the standard deviation of my sample means? It goes down. So now I'm still going 1.65 standard deviations to the left and the right, but if the standard deviation now is only 2 instead of 10, I'm going to have a much narrower confidence interval. So anytime you see a sample size increase, we can get a more narrow confidence interval. Well, that's great, right? We want to be able to narrow down where this true population mean is as close as we can. So, maybe up here I was like, oh yeah, the true average income is somewhere in between, I don't know, just gonna make something up, 50,000 and 100,000. I took a larger sample. If I found the same sample mean, building the same level of confidence, maybe now I can say that the true, I don't know. Oh, this wouldn't make sense. Hold on. So this would have to be 75. So maybe now I can say it's somewhere between 65 and 85,000, right? A much narrower range, right? And kind of I'm narrowing down, trying to figure out where this true population mean lies. So higher sample sizes, once again, always a good thing. This is just another example of that. And then this one might seem obvious, but if the variance or the standard deviation of the variable you're sampling from is higher, well, that's going to increase the standard deviation of your sample means. So anytime you've got higher variation in the data you're sampling from, you're going to have a wider, and sorry that my red markers aren't as wide and it died on me, but right. So those are the three things, right? Higher levels of confidence. We said higher levels of confidence or lower alphas will make you have a wider confidence. And that kind of makes sense, right? If I want to say something with 90% confidence, I can give you a much narrower range. But if I want to say 99, how can I make sure that I'm more likely to be telling you a confidence interval that includes a true population mean? Make it wider. So higher levels of confidence, lower alpha values, I'm getting wider confidence intervals. Higher sample sizes, they're going to become more narrow. Higher original variation in the data is going to give me wider. And that kind of makes sense. If there's a lot of variation in the data, then my sample is more likely to maybe not be reflective of the population as a whole. Okay. All right. So we kind of already went through all these, but here's like a nice summary of those three things. Okay. So let's work through a complete example, and then maybe we'll take a step back here, because we can do not only this for sample means, we can also do it for sample proportions we'll end up seeing. So let's say, this seems like a dumb example, but let's say we don't know how much the mean weight of hockey pucks are, right? So we got some manufacturer, and I don't know, maybe I'm the NHL, and I want to make sure that they're producing these hockey pucks at the weight that we wanted. We can't sample every hockey puck they've created, but we can sample 49 of them and calculate a sample mean. So I do that, I get 7.5 grams. Excuse me. If I wanted to build a 95% confidence interval for this population mean, what would I do? Well, I've got my, what do I need to solve this, right? Well, I've got my sample mean. I've got my population variance. So these all examples are all going to be kind of weird. Like, how do I know the population variance, but I don't know what the population mean is? For the sake of we're going to talk about more realistic examples later on and how we deal with the fact that we might not know the population variance. But there are a lot of examples like this where maybe I know the variation that exists on the machinery, right? And I just want to make sure that I'm producing the correct mean, right? So I know the variation that exists on the pour of the molds because of, I can do the physics and whatever. But for right now, just assume we know the population variance. We'll talk about the more realistic scenario where we don't later on. So I also have my sample size. I also know my alpha value here. So the 99% confidence interval, alpha will be 0.01. I've got half of alpha on each side of my confidence interval, so 0.005. That was where, when we went to the table, where's the table? There it is. If I want 0.005, we're kind of in between these two values. So negative 2.57, negative 2.58. In practice, generally, I always use kind of the higher of the two. You can split the difference and do negative 2.575, or we could use, once again, Excel, use that norm.s.inv, tell it 0.005. So I could say, okay, norm.s.inv, 0.005. Okay, 2.575. Yeah, I can be really precise. Now notice, these Z values that you're using, you should be getting pretty familiar with them as you work through more problems because they're always going to be the same. So when we're looking at these scenarios where I know the population variance, my Z value for 99% is always going to be 2.5758. For the 5% level, where I have half of alpha, 0.025 in each tail, always going to be 1.65. The final one, I think I mentioned this to you earlier, but not INV, or sorry, not this, the INV, 0.05, which would be an alpha of 0.1, right? It gets split up into a few tails. Always going to be that negative 1.644. So we should be getting kind of familiar with these values, but if you ever forget them, you can use Excel or you can look them up here in this table. All right, so we've got all the components that we need, right? We just looked up and found our Z-score associated with half of alpha in the tail. A lot of the times, I think it's probably easier to add in this step of, I can write it all in one formula, and I'll show you here in a second what that looks like. But I can also do this like as an intermediate step. So I can then calculate the standard deviation of my sample means. That's just the square root of the variance from the data we sampled from over our sample size. And then it's just a matter of plugging everything into our confidence interval equation, right? So in this example, what does that look like? Well, I write down all the things that I had, mean of 7.5, sample size of 49, population variance of 49, alpha is 0.01. What's z-score associated with half of alpha? Once again, we looked that up, 0.005. It was like 2.575, round that up to the second decimal, 2.58. Okay. What else? Oh, and then the third step here. Actually, one thing I want to point out before I keep moving. So I put in here 0.995. You can look it up either way. So if I look up alpha over 2 of 0.005, I'll find negative 2.58. I'm just looking at the flip side, right? If I wanted 0.005 in the right tail, right? Then when what area is or what's the cumulative probability to the left of that z-score of 2.58? Well, it would be 0.995. So I could look up 0.005 alpha over 2, or I could look up, that would always give me the negative value, or I could look up 1 minus alpha over 2. That will give me the number of standard deviations I need to go above and below, but just the positive. Okay. So then I'm going to kind of do this intermediate calculation where I calculate the standard deviation of my sample means. I gave you an easy one here. That ends up being 1. And then it's just a matter of, okay, take 7.5, add 2.58 times 1 to get my upper bound, subtract 2.58 times 1 from 7.5 to get my lower bound. And with 99% confidence, based off the sample mean that I took, only 49, of these hockey pucks, I can tell you with 95 or 99% confidence that the true sample mean weight for these hockey pucks is somewhere in between 5 and 10 grams approximately. Right? Now, what's one way I could maybe narrow this down more? Increase our sample size. Maybe say it with a little less confidence, maybe 90% confidence. And those are the things I can change. I can't really change the variation that exists in the machinery pouring these hockey pucks into molds. But if for some reason the machinery got better and we had less variation, that would also kind of reduce the size of our confidence interval. Okay. Let's just work through another example. I think seeing more of these is gonna just be helpful. So let's say I'm looking at the length of a pregnancy. I can look at some old historic data, and the population variance on the length of pregnancy is about 9 weeks. I sample 81, and I see that the sample mean average of those 81 births was 38 weeks. What's the 95% confidence interval for the true population mean of, this is for Indiana. Sorry, not for like the whole country, but for Indiana, gestation weeks or length of the pregnancy. Well, what are the things I need? I need 4 things. I need my sample mean, got that. I need my population variance of the data I'm sampling from, got that. Sample size, got that. Alpha value, well, 95%, that means that there's 0.95 within the confidence interval, means there's 0.05 outside of it, but I've got 2 sides, so in each one there's half of alpha or 0.025 in each tail. I then want to find the z-score that's associated with that. Right? So if I just look at these values, all of them kind of seem like, oh yeah, they're all built around 38. I can't really rule any of them out, but this might be like a potential problem I might give you like on a homework or an exam. So we identified those things that we needed. I said half of alpha was be have 0.05 outside the confidence interval. Half of that's 0.025. The z-score associated with that. Once again, I can do this 2 ways. I can look it up in the table. So where is 0.025? Right here. So negative 1.96. So I need to go 1.96 standard deviations below to get my lower bound, 1.96 standard deviations above to get my upper bound. Or I could use that norm to S to I and V function. I want half of alpha, 0.025 in each tail. So I'm going to go 1.96 standard deviations above below. Find the same value. Okay. Then from there, I can do the intermediate calculation. So if I had the population variance was 9, sample size is not 81, take the square root of that. The standard deviation on my sample means is 1/3. Now it's just a matter of plugging this in, right? So I can take that sample mean, add 1.96 times the standard deviation of 1/3 to get my upper bound, subtract 1.96 times the standard deviation of my sample means 1/3 to get my lower bound. And there we go. And I can say with 95% confidence here that the true length of a pregnancy, population mean is somewhere between 37.35 and 38.65 weeks. So I've got a pretty narrow range here. Why? Well, because I had a relatively large sample size. the variation that exists on the original data was relatively low, right? So I was able to kind of pinpoint down just based off of one sample, right, where that true population mean lies. Okay. Now, there is still a 5% chance that my confidence interval doesn't include the true population mean, right? We're building this at the 95%. So there is a 5% chance I'm wrong, but a 95% chance that the true mean is somewhere in this range. Okay. Um, just some more practice. We'll go through another one. So let's say I take a sample of 35. Maybe I'll actually show you a way you could kind of set this up in Excel and I don't know, make your life a little bit easier. So let's say I take 35 weight plates, 45-pound weight plates from the rec center, or whatever, I forget what it's called here, but basically the gym, right? And I find a sample mean is actually a 46.5. So when they pour these plates, that's actually true. You can weigh them out. Some of them are off by a pound or two. So let's say I took a sample of them, I found 46.5. We know that the true population variance is 25. There's something about the production process. We just know the population variance, even though we can't observe the population mean. Maybe if I'm the gym, I'm like, hey, am I getting weights that are too heavy? What's the chance that the real population mean is 45, right? So I'm going to build this confidence interval, which of the following would make sense. Now, we can rule one of these out right away. So if I look at this, my confidence interval has to be built around the sample mean I saw. My sample mean isn't even in this confidence interval. It doesn't make any sense. Right? Now, from there, if I wanted to go through and solve this, right, and I've got kind of the step-by-steps here, but I'll show you how I could do this in Excel. So I'm going to identify everything I need. Sample mean, 46.5, sample size, 35, variance of the original data was 25. Now here, I gave you the alpha. So let's work backwards. What level of confidence would this be? Well, if alpha is 0.1, then that's the area outside my interval. The area inside my interval is 0.9, or that's the decimal form of 90%. So this is my 90% confidence interval. Half of alpha is 0.05. I can look that up in my table, find 1.65 or negative 1.65. I can then do the intermediate calculation, plug in that population variance sample size. It's just a matter of getting this plugged into the formula. Okay. Now, kind of the key there is knowing that I need to use the z-score for alpha over 2. If I wasn't given alpha and I was just told a 90% confidence interval, I need to make sure I can figure out what the corresponding alpha value would be. But if I wanted to, I'm not going to give this to you, but if you created it for yourself, I'd be more than okay with this. So this is kind of a summary of the different confidence levels and alphas again. But you could do, let me see. So we'll start a new sheet. So, if you're watching these videos and you want to create something similar, this might be helpful. So let's say I put the sample mean, my sample size, the known population variance, and here I'm going to look at different values of alpha. Actually, no, I'll even do level of confidence first, right? So here I've got my 90, 95, 99%. What I can do is say, okay, look, I know I want this to be my lower bound. Here, I want my upper bound. I'm actually going to move this over a little bit so we have some things. So what are my alpha values, right? Well, alpha is just going to be the probability I see something outside of that confidence interval. So here, 90% chance I see something within the interval means that there's a 10% chance that I don't. So it would be what? 100 minus my confidence level. That will give me the percentage chance I see something outside the confidence interval. But these alphas we talked about are always in decimal form. So I'm going to divide them by 100 and move the decimal 2 places. Here I get my alpha is 0.1, 0.05, 0.01. I'm then going to think about, okay, what's the corresponding z value? Well, that's always going to be, and here I'm going to use this absolute value. So actually, before I do that, I'll show you first if we didn't use it. So norm.s.inv, we want to go a certain number of standard deviations away. That's going to give us not alpha in our tail, but alpha divided by 2. Hit enter. Now notice this is a negative value. When I actually go to type this in for my lower and upper bound, I want to just be using the number 1.65 or approximately 1.65. So we're going to use this thing called the absolute value function. right? With this absolute value function, it should just basically, all that means is it drops the negative sign. Now I'm going to copy this down, and I've got those three z values that we're always going to be finding for these conventional levels. Okay. I could then say, okay, well, look, what's my lower bound? That's going to be my sample mean. Subtract this many standard deviations. Now, what are my standard deviations? I could type this all into one cell. So I could say, well, that's going to be the square root of my population variance divided by my sample size. Okay. Now, I'm going to do something here to kind of show you, there's going to be a problem. If I want to copy, it would be really nice and easy. So I get my lower bound, and this will work here in a second, but there's a problem because I don't have any numbers here. So let's just make up some. So this is what, 46.5. I think it was what, 35 and 25 for that weight plate example. I'd like to copy this over, but all these cell references would change. So there's a couple different ways we could do this. So if you just highlight a formula, copy it. So I just did Command C on my Mac, Control C, I think, on a PC, and then click on the other cell and I paste. If I copy paste this way, it doesn't update any of the cell references. And all I want, the only thing I need to change for my upper bound is I'm adding that many standard deviations, right? So at the 90% level, I actually can't say the true sample mean for these weights is 45, right? 45 is outside of my confidence interval. Now, when I copy this down, right, I actually don't want anything to change here other than that Z value. So I'm going to go through Command T, F4 on the PC, Command T on the Mac, freeze everything except for that Z value. Same kind of idea over here for my, oops, I hit the wrong button. My upper bound. I could then copy these down. Notice, okay, now I'm getting my 99% lower and upper bound. So now, all I have to do, if I build this Excel file for myself, well, let's say I had something where the population variance was 100. My sample size was 34. Actually here, 47. Right? Sample mean is, I don't know, 243.65. Notice if I build this up, all I'm doing, I just have to identify what my sample mean, my sample size, my population variance are in every problem. And then, okay, what is my confidence interval? I need to know what level of confidence I'm looking for. Okay. What else do I want to say here? No, I think that should cover it. And you can break this down to be, I could break this down as steps. So instead of typing this all in one line, I could have like created a separate one where I have the standard deviation of my sample means, which is just the square root of population variance over my sample size. And then I would only have to put in like one cell reference here and not put in the square root just to make it a little bit easier to look at. It's really kind of up to you if you want to build this for yourself, exactly how you do it. Right? So I think that should cover it. Just wanted to prove to you and end this out. And then the second video, we'll look at sample proportions and when we don't, and when we don't know the population mean. So I had this file and now, oh, give me a moment here. I had it open. There we go. So I actually just don't have to prove this to you. What I'm saying is true about confidence intervals. And we did something similar when I was looking at the sampling distribution. Zoom in so we can see what I'm doing. So all I did here is I had that same, I showed this to you for the sampling distribution. I have like all these different letter grades for a bunch of different students. In fact, how many students do I have? Well, I use that count function. I've got 431. The true population mean, like this is all of my previous stat students. I can calculate the population mean. I can also find the true population variance, right? I'm then going to take 1,000 different samples, right? So this is where I just kind of generated a random number, then went to that student ID, plugged their grade in, and they're all of size 50. Okay. Now I'm going to set the alpha value up here to be 0.01. Right? So it should be that if I were to build confidence intervals for every single one of these sample means, right? Every one of these samples would have their own sample mean. I should have that 99% of those confidence intervals, 99% include the true population mean of 79.8. So what did I do down here? Well, if I've got my samples, I just found my sample mean, or the average for that sample. How do I find my lower bound? Well, I just took my sample mean. I then found how many standard deviations away do I need to go? Well, this is a little bit tricky, but I want to find just the positive value. So instead of using the absolute value, I use this little trick of 1 minus alpha over 2. You don't have to do that. You could have used the absolute value, but essentially this is finding me the z-score that's associated with alpha, which was up here, right, divided by 2. I then multiply that by the standard deviation of my sample means, which is just the square root of, I can scroll up, the population variance over my sample size, right? So I build my lower bound, same idea, except I add that many standard deviations to get my upper bound. I'm then going to use something, and then copy that over. I build a confidence interval for every single one of these different sample means. I then created this thing, which is a little bit tricky. I wouldn't expect you guys to do this. We haven't looked at this yet, but I can use these if statements in Excel and say, okay, look, if this is true, put this number in the cell. If this is not true, put this number, right? So I said, okay, look, if that true population mean, scroll up here. So if that true population mean, is less than my upper bound, then I would like to check something else, right? If it's not, if that population mean is not below my upper bound, that would mean the population mean is outside of my interval. I want to put a 0 here, reflecting that no, this was not my true population mean was not in this confidence interval. If that population mean was below my upper bound, well, the second thing I need to check is it greater than my lower bound, right? I need to see, is it somewhere in this confidence interval? If it is, well, then it's, now I've got a sample mean that's, sorry, I have a population mean that's below my upper bound, above my lower bound. So it's in the interval. I'll put a 1 here. If it's not, right, if it's lower than my lower bound, I'll put a 0. So that's all that's doing. So notice here, okay, is that true mean of 79.8? Not quite in my interval, so I get a 0. But here, 79.8, oh, definitely in this interval, definitely in this interval, so I'm getting 1s. So what I'm going to do, I'm just going to add up this row because that would tell me the number of confidence intervals I have here where the true population mean was in the interval. I'm then going to say, okay, look, I'm just going to use the count function. Now I knew this ahead of time. I could kind of cheat, right? I knew I have 1,000 samples, but I use that count function to say, okay, I've got 1,000 samples. 989 of them have the mean, the true population mean within that confidence interval. So just take how many had the true population mean in the interval divided by the total number of samples, multiply it by 100 to get a percentage. Here, exactly 99% of them. Now, as I change these numbers, notice, okay, this one's a little bit off. Now, once again, I've only got 1,000 samples to really prove, fall in line with the exact mathematics. I'd have to have an infinite number. But as I play around with this, I can see it's always kind of floating right around 99%. Sometimes it's a little bit higher, sometimes it's a little bit lower, right? But, if I'm building these confidence intervals using that formula, I could play around with this. I could change my alpha to 0.1. Now it should be that 90% of my confidence intervals include the true population mean. Close, 91.6. Oh, just below 90, just below 90, right above 90. So it kind of floats around. Once again, it's because we only have 1,000 different samples and not an infinite number. But I don't know. I thought this is kind of a nice little easy way, first of all, to show you kind of the extent or the kind of how far you can push Excel. We're not going to use these if statements in anything that any problems you have to do. But I just think it's a nice kind of easy way to see what we've been talking about with some actual data. And here I could kind of cheat, right? I had the population data and then I was taking samples. In practice, we couldn't really do this because we often only have like one sample. Okay. All right, so that should do it for this video. The next one will kind of continue looking at how do we do confidence intervals for two other scenarios.